Welcome to another AP Calculus video. Today I'm going to be showing you information about extreme values of functions. By the end of this video, hopefully you will understand and explain the extreme value theorem, which means you're going to be able to explain when a function must have both a maximum and a minimum. We're going to try to find the maximum of x squared and where it occurs, the minimum of x squared and where it occurs, but we're also going to be talking about vocabulary. If you're watching this video, I know you know what x squared looks like. And here we go. In lower level classes, a lot of teachers say, okay, this point down here, 0, 0 is the minimum of x squared, and call that a day. That's not false, but it also doesn't give all of the information you need. You might be asked something a little more specific. When we say, well, let's just work on the minimum. What is the minimum of y squared? I'm sorry, y equals x squared is, well, we all know that's going to be 0. But is that x equals 0 or is that y equals 0? Well, a minimum is the smallest y value that a function, contains. This is a y equals 0. So the minimum of x squared is y equals 0, which occurs at x equals 0. Whenever you're given an at, a place, that's about an input. So what about the first question? What is the maximum of y equals x squared? What is the highest y value of y equals x squared? The maximum of y equals x squared does not exist. Or you could say y equals x squared has no maximum. So you might think, well, infinity is a maximum, so y equals infinity maybe. Okay, well, I can think of a bigger number. How about infinity plus 1? No, that's larger. What about infinity plus 1 to the second power? When we say maximum, we mean one particular number. And since x squared grows to infinity, x squared doesn't have a maximum. So our goal is to show when a function must have a maximum, must have a minimum. So we're going to bound x squared on the closed interval -3 to 2. Let's sketch that. Okay, so maybe we can label y equals x squared. And so, does x squared have a maximum? It sure does. So the maximum of x squared on the closed interval -3 to 2 is 9. That's a y equals 9. Don't forget, the maximum is the y value. Okay, so I'm going to say the maximum of x squared on the closed interval -3 to 2 is 9, which occurs at x equals -3. Okay, you might be wondering why I put in that closed interval. Well, let's think about this. The maximum of x squared is 9. Is that true? It's not. We just said that the x squared has no maximum. So why does x squared have a maximum right now? Because we're talking about that particular closed interval, -3 to 2. The minimum of x squared, do you know what I'm going to write? So I am going to include that closed interval, -3 to 2, because that's the question I was asked. So the minimum of x squared on -3 to 2 is 0. By the way, that's y equals 0. And that occurs at x equals 0. Okay, so originally x squared didn't have a maximum, although it had a minimum. And this time x squared did have a maximum and a minimum. Let's see if we can tease apart what we did. Let's see something else. So we're still looking for a maximum and a minimum. We're still talking about x squared from -3 to 2, but what's different? We're talking about open endpoints. X squared is not defined at -3, but it is defined at -2.9, -2.99, and so on. So let's tackle the easy thing, and that's the minimum. The minimum of x squared on -3 to 2 is 0, which occurs at x equals 0. Nothing is changing here. The maximum is a little bit weird. So we know, see if I can get a different color here. Nope. We know the maximum of x squared has to happen somewhere up here. Those y values are much larger than the y values down here. So let's think about this. What's the highest y value that x squared attains? Well, y equals 8. Can you think of a higher one? Y equals 8 is definitely on this graph. Can you think of something higher than y equals 8? How about y equals 8.9? Is that on this graph? Sure is, right up here. So that's higher than 8. Can you think of something higher than 8.9? How about 8.99? Yep, that's even higher. I don't know if I can draw that even closer. 8.999 is equal to y. That's higher, sure. What about y equals 8.999999999? Is there one particular highest y value? Weirdly, no. No matter what number I write, 8.99999, you can always put another 9 in that next decimal place, and we have a number closer to 9, but not 9 itself. Wait, why don't I just say 9? Well, because y equals 9 is the height of this hole up here, and x squared is not defined at -3, it's only defined just to the right of -3. So y equals 9 is out. What does that mean then about the the maximum of x squared? Y equals x squared has no maximum on the open interval -3 to 2. Let's go back and look at that again. The first example, we had all of x squared, and that graph, that function, had a minimum at 0, but no maximum because both ends grow to positive infinity. Or the end behavior is positive infinity on both sides. When we changed x squared to only being defined on a closed interval, -3 to 2, a maximum and a minimum were both found. With an open interval, we could find a minimum, but we couldn't find a maximum. I think it's time to look at a new function. Okay, y equals 1 over x looks like this. And what highest y value does 1 over x have? Y equals 1 over x has no maximum. Since 1 over x grows to infinity near or as x approaches 0 from the left-hand side, y equals 1 over x has no maximum. What about a minimum? Well, y equals 1 over x also has no minimum. To the left of 0, 1 over x drops to negative infinity. Well, it worked last time. Let's try our same closed interval. 1 over x on the closed interval negative 3 to 2. Can we find a maximum? Can we find a minimum? So we know what 1 over x generally looks like. Let's see, what's that point going to be at the end? How about 2 1/2? And we still get unbounded growth to the right of 0. And negative 3, negative 1/3 is the other endpoint. So what's the maximum of 1 over x? Oh, on the closed interval negative 3 to 2. Yeah, still no maximum. And still no minimum. So it's not just a closed interval. When we were talking about x squared, the closed interval did everything we need. So what do you suppose is breaking this idea of guaranteeing a maximum and a minimum? We tried the closed interval we had before. Well, maybe we can come up with some examples. So there's 1 over x. Let me see if I can get another color. Nope, they're the subtitles. Okay, let's keep this endpoint of 2. I can make that a right-hand endpoint. Let's choose another value where 1 over x would have a maximum and a minimum. How about 1? For sure. If we're just talking about 1 over x on the closed interval 1 to 2, 1 over x has both a maximum and a minimum. Can you think of any other intervals? Let me get my yellow back. How about an interval starting at 1/2? So from 1/2 right here, all the way up to, would 7 give a maximum and a minimum? It sure would. What graph would we have then? Something like this. You got to ignore this piece off to the left. That part of 1 over x definitely has a maximum, which occurs at 1/2, and a minimum, which occurs at 7. Okay, let's try an interval to the left of x equals 0, or at least that involves a negative number. So how about, previously I think we started at negative 3. So what would a good right-hand endpoint for that be? Hopefully you're thinking anything works as long as we're choosing a number to the left of 0. So even if you did negative, oh no, don't end showed, negative 0.1, that would be something like this. Oh, maybe even closer. And that part of 1 over x on the closed interval negative 3 to 1/10 would definitely have a maximum at negative 3 and a minimum at negative 1/10. Can you put that all together? If you can, you already understand the extreme value theorem. So the answer to what the extreme value theorem is what must be true of a function for an absolute minimum and absolute maximum to be guaranteed? Well, we found some intervals here. It's not just a closed interval on a function. It's not no interval. Definitely not an open interval. So what are we talking about? A function is going to have an absolute maximum, meaning one highest y value, and an absolute minimum, one particular lowest y value, if the function is continuous on a closed interval. So that's what we were doing on the last example. As long as you're talking about part of a function that's continuous on that entire interval, even if it's discontinuous somewhere else, that function on that closed interval will be guaranteed to have a maximum and a minimum. The reason that's important is if you're ever asked on the AP Calculus test to find an absolute maximum, to find an absolute minimum, you're going to be given a continuous function on a closed interval.